As dozens of executives, engineers and dignitaries stood on the factory floor of Packard's East Grand Boulevard plant, the roar of two 12-cylinder engines drowned out every other sound. People had traveled across the city to witness what looked like another wartime demonstration, but the tension between the men in dark overcoats told a different story. On one side of the room were Rolls-Royce engineers, guardians of the Merlin engine, a power plant that had saved Britain in the Battle of Britain. On the other side were Packard engineers who believed that Detroit's assembly lines could build better machines than any craftsman's bench. When the throttle levers were advanced and the engines bellowed to life, there was no applause. There was only a silent question hanging in the air. Could American mass production create a miracle without destroying a British masterpiece? The question had life and death consequences. By early 1942, American bomber crews were flying deep into occupied Europe in formations of B-17 flying fortresses cruising at 25,000 to 30,000 feet. Their escorts, North American P-51 Mustangs, were fast and agile at low altitude but weak above 15,000 feet because the Allison V1710 engine's single-stage supercharger struggled to provide adequate manifold pressure in thin air. The P-51's Allison delivered around 1,150 horsepower at 11,800 feet, and the aircraft's top speed at about 15,000 feet was roughly 390 miles per hour. German fighters operating in thinner air simply climbed above the escorts and attacked with impunity. Without a fighter capable of matching the bomber's cruise altitudes, the 8th Air Force bled. On a single mission in August 1943, 60 bombers were destroyed. The P-51's airframe was a masterpiece of aerodynamics, but it needed a heart transplant. Across the Atlantic, Rolls-Royce had a solution. The Merlin engine, designed by Sir Stanley Hooker, featured a two-speed, two-stage supercharger that maintained sea-level pressure up to around 30,000 feet. In the Merlin 61, the two-stage supercharger could be shifted from a 6.391 to 1 gear ratio to 8.095 to 1 via an oil-operated clutch, delivering 1,390 horsepower at 23,500 feet. In Spitfires and Hurricanes, that system allowed Allied pilots to climb and dive across the sky at altitudes the Allison engine could only gasp at. There was just one problem: the British could not build enough Merlins. The engine contained about 14,000 individual components, each subject to tolerances measured in 10,000ths of an inch. Rolls-Royce factories at Derby, Crewe and Glasgow produced roughly 200 engines a week when they needed more than 10 times that number. When German bombs rained down on Britain in 1940, the Ministry of Aircraft Production looked west. Could American factories build Merlin engines without sacrificing the precision and craftsmanship that made them special? Rolls-Royce selected the Packard Motor Car Company and signed a $130 million licensing agreement in September 1940. Packard had experience building luxury automobiles and had produced the Liberty V-12 aircraft engine in the First World War. What made Packard attractive was not just experience, but process. The company sold nearly 98,000 cars in 1940. Rolls-Royce's entire automobile output between 1936 and 1939 was just over 6,200 units. Packard knew how to produce precision parts on assembly lines where any crankshaft would fit any block, any piston would fit any cylinder. That interchangeability was foreign to Rolls-Royce, where skilled craftsmen hand-fitted connecting rods, filed bearings and adjusted clearances on each engine. Rolls-Royce engineers delivered crates of Merlin engines and thousands of blueprints to Detroit, confident that their methods were superior. When the American engineers unrolled the drawings, they were stunned. The blueprint called for British standard Whitworth threads, a 55-degree thread form with radiused roots and crests, whereas American manufacturers used a 60-degree unified thread. Every bolt and nut on a Merlin used Whitworth forms, including coarse BSW, fine BSF, British Association, BA, and British Standard Pipe, BSB. Rolls-Royce had used these thread systems since the 19th century, and the drawing list contained no tolerance data for many of them. Experienced fitters simply cut threads, measured them, and filed as necessary. American factories had no Whitworth taps, dies, or gauges, and American machine tools were built to U.S. thread standards. Measurements on the drawings were specified in fractional thousandths of an inch derived from the imperial system, but not necessarily aligned with U.S. manufacturing practice. Worse, many dimensions assumed that parts would be hand-fitted. Rolls-Royce craftsmen expected to remove material with files or adjust bearings with shims. Packard did not tolerate such improvisation on an assembly line. The first meeting between the teams captured the rivalry. A Rolls-Royce engineer reportedly asked if the tolerances on the drawings would be too challenging for the Americans to achieve. The Packard engineer Jesse G. Vincent replied that the problem was quite the opposite. The tolerances are far too wide for us. We make motor cars far more accurately than this. Every part on our car engines has to be interchangeable with the same part on any other engine, and hence all parts have to be made with extreme accuracy, far closer than you use. That is the only way we can achieve mass production. The British engineers fell silent. To them, Packard's confidence bordered on arrogance. To Packard, Rolls-Royce reliance on handcraft was archaic. The stage was set for a silent duel of philosophies. Packard engineers decided not to copy the Merlin, but to translate it. Over 11 months they redrew virtually every component, producing around 6,000 new technical drawings. Each dimension was converted from British specifications to American manufacturing practices. Each tolerance was tightened to ensure interchangeability. When Rolls-Royce specified a crankshaft main journal diameter as 2.25 inches with permissible variation that could be corrected by filing, Packard re-specified it as 2.2495 inches with a tolerance measured in 10,000ths. Detroit insisted that if a crankshaft left the factory, it would fit any block without modification. The American team also re-engineered components to improve durability. Rolls-Royce copper lead crankshaft bearings were replaced with a silver lead alloy plated with indium, which improved load-carrying capacity and break-in characteristics. Initial British objections faded when testing showed the new bearings lasted longer and ran cooler. The thread problem was perhaps the most symbolic of the rivalry. Packard could have converted the engine to American thread standards, but that would have made spares incompatible with British aircraft already in service. Instead, they did something unprecedented. They built or ordered Whitworth taps, dies, and thread gauges in the United States, even though no American toolmaker produced them commercially. Machine shops were equipped with special cutters to reproduce 55-degree thread forms with radiused roots, and machinists were trained to use thread standards most had never seen. Every fastener in a Packard-built Merlin used the same British specification as a Rolls-Royce-built engine, yet Packard manufactured those threads to tighter tolerances. A bolt made in Detroit would screw into a nut made in Derby without any fettling. This dedication to compatibility foreshadowed a post-war move toward a unified thread standard. After the war, the United States, United Kingdom and Canada adopted the Unified Thread System in 1948 to prevent the logistical problems caused by differing thread forms. The supercharger offered another arena for innovation. Rolls-Royce balanced the two impellers by hand, adding or removing tiny amounts of material until the rotor spun smoothly. Packard developed precision casting and machining processes that produced impellers with such consistent geometry that minimal hand balancing was needed. American engineers built test rigs that measured dynamic balance while the impellers spun at operational speeds exceeding 30,000 revolutions per minute. Cooling passages cast into the supercharger housing were redesigned for more efficient flow, and a centrifugal pump circulated ethylene glycol coolant at 36 gallons per minute to keep intake temperatures under control. The two-speed, two-stage system maintained boost at altitude, but Packard refined its manufacture so that each gear train engaged smoothly and reliably on an assembly line. Even outside the engine's core, Packard's influence was profound. Cylinder heads and blocks that had been individually matched in Britain were machined to standard sizes and assembled interchangeably. Carburetors were fitted with American-made Bendix injection units that used U.S. thread standards but mated seamlessly to the British spec intake manifolds. Special jigs and fixtures ensured that every connecting rod big end was identical. Statistical process control charts tracked the diameter of piston pins and valve stems. The factory floor itself was redesigned to accommodate dedicated machining centers, one for crankshafts, another for milling block faces, another for valve seat grinding. Gauges and micrometers measured every dimension. Any part outside tolerance was rejected, not reworked on a bench. All of this engineering went on under the watchful eyes of Rolls-Royce observers who sometimes winced as Packard removed the mystique from their beloved engine. Yet results began to speak louder than tradition. The first two Packard-built Merlins ran on August 2, 1941. The demonstration engines purred at test stands in Detroit while British and American engineers listened for the slightest vibration. They heard none. Rolls-Royce engineers returned to Derby with samples of Packard's silver lead bearings and adopted them quietly for later production runs. Detroit's manufacturing discipline even informed Rolls-Royce's own expansion. By 1943, the British shadow factories had mechanized their operations to boost output, acknowledging that in total war, artisanry alone was not enough. Full production at Packard began in 1942. By the following year, the Detroit plant was turning out around 400 engines per week, more than Rolls-Royce's entire British output. In total, Packard built 54,714 of the 55,511 American Merlins for the U.S. Army Air Forces, with Continental supplying the remainder. Including engines supplied to Britain, Packard manufactured around 55,523 Merlins under license. Many were variants of the Merlin 60 series, designated V16503 and V16507, which included the two-stage supercharger that Stanley Hooker had designed. These engines delivered more than 1,270 horsepower at 30,000 feet and could sustain over 1,500 horsepower in takeoff power at lower altitudes. The V16507 produced around 1,695 horsepower at maximum RPM, and when installed on the P-51 Mustang, it propelled the fighter to 437 miles per hour at altitude and gave it a service ceiling above 40,000 feet. The transformation of the Mustang was immediate and dramatic. A single-stage Allison-powered P-51A could reach a maximum speed of 390 miles per hour at roughly 15,000 feet and delivered its peak power below 12,000 feet. With a V16503 or V16507, the P-51B and P-51D could climb to 28,100 feet and still achieve about 440 miles per hour. The two-stage supercharger allowed the engine to maintain 1,390 horsepower at 23,500 feet, giving the Mustang the power to escort bombers all the way to Berlin and back. Pilots described the high-altitude performance as revelatory. Where the Allison engine wheezed and lost power, the Merlin roared and pulled. German pilots quickly learned to fear the silhouette of the P-51 at altitude. Instead of diving down on the bomber boxes and escaping unmolested, Luftwaffe fighters found Mustangs waiting above them. The engine produced a distinctive howl that bomber crews came to regard as the sound of salvation. As production ramped up, the rivalry between the engineers mellowed into mutual respect. Rolls-Royce engineers admitted that Packard's statistical process control and dedicated tooling produced engines with more consistent performance. Packard engineers acknowledged that without the fundamental brilliance of the Merlin's design, Stanley Hooker's two-stage supercharger, the 60-degree V12 layout, the efficient coolant pathways, there would have been nothing to mass produce. The story ceased to be about who built a better engine and became one of complementary strengths. To this day, historians debate whether Packard engines were inherently superior to Rolls-Royce versions. The answer is less important than the fact that each side pushed the other to new heights. The legacy of this rivalry extends beyond the war. Modern jet engines and turbofans are manufactured on principles developed in those Detroit workshops: precision casting, statistical process control, dedicated machining centers, and rigorous interchangeability. The bearing technology Packard pioneered, the silver lead alloy with indium plating, became standard in high-performance automotive engines. The logistical headaches caused by multiple thread systems prompted the United States, United Kingdom and Canada to agree on the unified thread form in 1948. That standardization eventually evolved into international screw thread standards, ensuring that a bolt made in one country will fit a nut made in another. And the philosophical lesson remains potent. Mass production and precision craftsmanship need not be opposites. They can be merged when engineers respect the intent of a design while reimagining its execution. A few Packard-built Merlins still run today. A Lancaster bomber at the Canadian Warplane Heritage Museum flies with 4 original Packard V1650 engines. In air races at Reno, highly modified P-51s with Packard Merlins produce more than 3,800 horsepower, nearly 3 times their original rating, a testament to the robustness built into those wartime engines. When enthusiasts hear the distinctive howl of a Merlin at an air show, they are listening to the echo of a conflict and collaboration that changed history. The roar that shook Packard's factory on August 2, 1941, was more than a test run. It was the sound of two engineering cultures challenging each other and, in the process, crafting a machine that transformed a war.